Bem-vindos to one more episode of the Type Theory for All podcast. As always, this is your host Pedro Abreu, and in this episode we continue our conversation with Jan de Muijnck-Hughes, a research associate at Glasgow University. He works using all sorts of fancy type systems, mostly targeted for hardware specification, in particular with the aid of the theorem prover Idris. In this episode, we start by talking a little about imposter syndrome in academia and how he has learned to cope with it. And then we finally dive deeper into the technicalities of his research. For example, we talk about session types, graded types, quantitative types. There's so many cool types that I don't even remember all of them to list here. Before we get into this episode, I'd like to invite you, my beloved listener, to join our Discord server. That's right, we have a Discord server now. And it's supposed to be an inclusive hub for anyone with any kind of interest in type theory to talk, share ideas, ask questions, all this cool stuff. If you have any dumb questions, then you'll be in the right place because I have so many dumb questions about type theory. So if that is something that you would be interested in, go to our website, Type Theory for All. You will find a link with an invitation to the Discord there. And not only that, if you are a subscriber, if you contribute to the show with any amount, even $5, $3 will do, then you will gain exclusive access to a channel in this Discord to send questions to our next guest. That's right. So, for example, our next guest is Leo de Moura, and he's the creator of Z3 and Lean. You'll probably know him. So if you're a contributor, you will be able to send him any questions you want. So go to our website, typetheoryforall.com, join our Discord server, and if possible, become a subscriber and gain exclusive accesses. So let's get into this episode. All right. Welcome back, everyone, to the continuation of another episode of the Type Theory for All podcast. This is the first time we're doing this, getting the same episode in two different parts in different days. So now we are refreshed again and we can go back into looking into all the cool things. Thanks a lot, Ian, for being here again.
No, it's fine. I think if you give somebody an inch, they'll take a mile. And so it's good to talk about a lot of things. And it was nice talking about problems in academia because I don't think we talk about them as much as we should do.
Yeah.
Or if we do talk about them, it's always in hushed corners, and have it out in the
Right.
open, I think is just quite good. But now we can start doing more technical talk because, it is a type theory podcast after
all. Sometimes I keep thinking, trying to think of how my listener thinks. And, there are different kinds of listeners. I know there are some people in the industry. There are some, late undergrads. There are some PhD students. So I feel that parts of these things of academia is not super interesting for everyone. but it's super important for everything that we do here. So I just keep bringing them over here. So one thing before we get into the more technical questions that I definitely want to discuss, there is still some points that I would like to bring up, which is, academia is hard and there's no way around it. And the way I look at it, in academia, we are always surrounded by extremely smart and competent people. And it's impossible for us to not, even in the back of our minds, it's impossible for us to not compare ourselves with each other.
No, that's true, yeah.
My question for you is, what are your thoughts on imposter syndrome and feelings of inadequacy and even coping with failure? I believe that when you are introducing yourself, you have talked a little bit about a few cases of burnout throughout your career. What have you learned from this, and what are your current thoughts?
So it's like, realistically, I think we all have a little bit of imposter syndrome, everyone, and it's to the degree that you keep the wolves at bay will determine how well you can do in academia. Now, the thing is that this is essentially a mental health issue, and to make it very clear that if you are struggling, please find someone to talk to. There's lots of good mental health charities out there. And if you are struggling, it's the hardest thing you can do there is to ask for help. And I just want to reiterate, there are organizations in the UK, there's Samaritans, there's Mind, uh, universities will have student support services, or if you're faculty, there will be faculty support services. And not all of them will be great, but I just want to reiterate, and it's always good to reiterate, that there are services you can avail yourself of to help you with your mental health issues, be it imposter syndrome, feelings of isolation, failure, because they can and do impact upon your ability to do the job. And one of the biggest things that I've had over the years is imposter syndrome, isolation, and failure, feelings of inadequacy. And there's no easy way to talk about it. And I don't like talking about it often because it shows a vulnerability. And we don't like talking about vulnerabilities, but it's good to highlight them. So when I was doing my undergraduate, I was quite, high flying. I was doing well in my exams. I was doing well socially to a large extent. I was having fun, and that was great. And when I went off to do my master's, I went off with this feeling of I did my master's at, I did my undergraduate at St Andrews, went off to do my master's at Nijmegen in the Netherlands, and I thought, okay, I'll just be as high flying as I were. But I just ran into this big brick wall, sorry, of they assumed different things about my background based on their own experiences. And so suddenly, the degree I had and the background knowledge I had from that didn't cover everything that everyone else knew. And so I failed exams. It took me a couple of times to pass some courses that I actually really liked because I just didn't have the right background. And I went from this high flying notion of I can do I can do not even just academia, I can do my studies, to falling flat on my face, being in a place where I was actually incredibly isolated from colleagues and students. Now, part of that is because I was in a special master's course, which was spread across 3 different universities, which is really great because all the universities sort of came together to sort of share their specialist courses to offer a master's. Okay, but the problem was all the students were from the different universities, and when I started, I just so happened to be one of the few students doing this course, and so all my my main courses were at 2 other different universities, and I was seeing those people, but only on Mondays and Fridays, and the rest of the week I was quite alone because all the local courses were full of people you just couldn't really, well, no, not you couldn't really interact with, but uh, it was harder to break ice because you only saw them for maybe 1 or 2 hours a week, and then as soon as lectures finished, everyone fucked off, right? And it was hard to bring in. So, you got this, like, I was living in not a different country. The Netherlands is like a second home to me, but it was, starting to feel really isolating. And it really affected my ability to do my master's, right? And it was only till the last 6 months to a year that I finally found a group of friends who, I could see regularly, we had chats with. I still see them every so often now. We go in and out, like, it's quite orbital, our friendship. When I'm in the Netherlands, I see them. When we're out in the Netherlands, don't really speak to each other, but that's how friendships can be. They can be quite orbital. But that really knocked me, and thinking I can't do this job. I got accepted to my PhD in St Andrews, and to be frank, I disappeared for a couple of months because I was doing my master's thesis. I thought I got into my PhD program. All I had to do was finish, but there was like time constraints, and that was just a really confidence block. And I don't think I've actually really recovered from that, of being this high flying student. I'm not saying I was the best. I didn't get the best grades when I was undergraduate, but I was really competent, to going to failing exams, to feeling isolated, and that was just shit. And so when I started my PhD, I was like trying to boost myself up, trying to get in, and I was in St Andrews. It was that is home for me, and things got better, but it was just still feeling that isolation just really hung on, and that notion of failure still hung on, being able to do the work. And at the time, the PL group was getting quite well. It was more of a functional programming group at St Andrews, but I was there as well, and it was just, I got better and better. But then when I started doing the PL work, which I hadn't done before, I was learning it at quite a late stage. And so I didn't do undergraduate courses on PL. I didn't even do graduate courses. I read TAPL. I read the Springer books on PL. I found course notes to read. And so in the back of my mind, I still have this notion of, I don't know this stuff. When I go sit down and write a typing rule, I go, this is the way I think it should be done. And then you send it off for review and somebody says, well, that's not how it's supposed to be done. Your notation is not right. Your ideas are not right. And, or this is actually just shit work. And that if you're feeling, if you're feeling inadequate and being able to do the job, getting these bad reviews just really push you down. You think, well, what the fuck am I doing here? Can I do this job? Can I actually do the work? And one of the greatest tips I got from Edwin when I started getting, I got a really, really, really bad review. It was very direct. He basically said, look at it on day one, go away for a couple of days and reread it and try and work out what they were trying to say and what's the good part of it. But there's a bit more than that, right? Because if you keep on getting these bad reviews, it sort of stacks up and saying, well, can I do this? Or if you sit in talks, right, and you hear somebody talk about some concept, so it could be like gradual typing, it could be bidirectional type checking, session types, some really formal stuff, and you're sort of in the PL world, but you're not in the PL world, and you don't know the basics, can you put your hand up and say, actually, I don't know this? And somebody goes, well, this is just standard knowledge, right? And that is, that can also be embarrassing. So you're sitting there at the back of the room going, right, I'm supposed to know this stuff, but I don't know this stuff. Yes, I can go off and read it, but, what else am I missing? How do you know what you don't know? And then more than that is you still have to do your research. And it's a technique that you have to learn is to do it. But one of the sad thing is that I still feel inadequate. I still feel half the time like a failure because I was getting papers rejected for 3 years straight. I couldn't think I could get an academic job. I wasn't necessarily enjoying the work I was doing, not because I couldn't do it, but because I couldn't get published. And so what's the point in working on something and having this backlog of unpublished papers that you just couldn't get published? And so what's the point of doing your work if other people don't like it? And so what do you do? And there are many routes out of this. And I'm not going to say there's one definitive route of what you can do. There's no one little trick. You have to work out what works for you. And one of the things I did in the early days of starting my postdoc, and that was switching from doing my own research to somebody else's research, is I found people I could talk to. Not online, but in person. And so I was at the University of Glasgow, or still am, and there isn't a strong dependent types group there. I was, the expert in quote unquote on using Idris and doing dependent types that I was aware of in the section I was in. And so I thought, right, what do I do? Right, I'm going to go somewhere else. Not move jobs, but find a group. And this is I was really, really fortunate in that Scotland is one of the best places to do programming languages research. Not because it's got one great research group, which, to be frank, informatics thinks they are it, but they're quite big. That's LFCS, but it's because you're in commuting distance of Edinburgh University, Heriot-Watt University, Glasgow University, Strathclyde University, St Andrews University, Dundee University, Stirling University, the west of Scotland as well, Aberdeen at a push. And when you look at that, Edinburgh has a strong group. Edinburgh's got PL research, Glasgow's got PL research, Strathclyde's got PL research, St Andrews got PL research, but good, strong people doing interesting things. And so I try to reach out. And one of the nice things about Scotland is you've got this SPLS, which is the Scottish Programming Languages Seminars. And I think it was modeled after the Northeastern programming language seminar that you have in the Northeast of America. My history, we need historians in PL to tell us where these things exist. And so, I started surrounding myself, finding people I could talk to. But that's not always enough, because you start going to people's talks. You sit in a talk by, say, Bob Atke, and he shows you some category theory related to quantitative typing, and you go, oh my God, I have nothing here. Or you sit in something that's an AGDA talk, and you go, well, I don't even know what these symbols are, right? That's joking aside, but you do something and you go, well, actually, what am I still? And so you find people, and you still have these feelings of inadequacy, because you're out your comfort zone. But it's good to be out your comfort zone. But the trouble is, it can be a bit too much. And so what you need to try and find yourself is ground yourself, find people who work on similar things to you, reach out to them, and do that. And I did that during the pandemic. I was struggling quite a lot in not just my work, but in being a father. I have children. And I can't remember who reached out to who, but I was shouting to the abyss that is Twitter, and a few people in the UK PL community sort of said, yeah, we can have a chat. Let's have a chat and help me. And I talked to them. I ended up talking about work, which is a bit bad, but we also talked about being parents in academia. What's the trouble? And that's really helpful, right? And I think that's one of the key things is, for me, what is helpful is chatting to people, getting it off my chest, putting it to the back of my mind, writing it down, and moving forward, and trying it not to overcome you. But there are days where I can just think, actually, I can't do this job. It's not that I can't master LaTeX, it's just what I'm typesetting. I know somebody from that community is going to look at it and say, this is non-standard, this is crap, why are you doing this? Why are you doing this approach? This is not the right approach to do. But not in a way that says, I can understand it and saying, actually, I'm wrong, but just being saying, well, look, I disagree with you, but it's a bad review, it's a bad comment. It's saying, and I've had that, I submitted somewhere and saying, look, why should I learn Idris? Why should I do this? There's this other work here that exists. Why aren't this is good enough? Why are you doing it your way? And you think you need to be able to defend that in your writing, but you think you do. But then somebody says, well, that's still not good enough, right? And that's really hard, and it does impact upon your mental health. And I think there's other aspects here as well, which is, right, if you're struggling at work, find people to talk to. And at the end of the day, there's no real easy way out. And there's this lovely joke from Aaron, not joke, but story from Aaron Sorkin that he has in The West Wing and in his other show that he had before The West Wing, and I can't remember it. But anyway, it's if you go to the episode Noel in season 2 after Josh Lynham is shot and he goes into therapy, the lovely story is done by the elder character, and I can't remember his name, but it's basically, if you fall down a well, some people are going to go to the top of the well and say, right, I'm going to fetch someone, I'm going to help. I'm going to fetch someone, like you see a member of the cloth, religious people, so on, so on. And then the guy's best friend comes in and says, right, jumps in the well and says, right. And you ask, why did you jump in the well? And it's like, I've been here before, I can show you the way out. And this is a very bad paraphrasing of the quote, but it's a wonderful quote of saying, look, find yourself with people who've been there that can help you get out of that hole that you're in. Right? And sometimes that's by talking, sometimes it's just having a good group of friends, and sometimes it's having a good work-life balance. Find people who can help you find to be who you are and not necessarily let you get on, because it's okay to feel shit. It's okay to feel fucking terrified. It's okay to be struggling. But what's not okay is for that to be the be all and end be of who you are. And you need to push through that. And you need to surround yourself. And I know there's people in the PL scene in North America and they're having a very shit time. And as a bystander, there's not much much we can do. We need to change as a community. People need to leave communities if it's toxic. But it's like the best thing we can try and do is surround ourselves with people who can help you get out the pit. And that's, I think, more or less say like the failure thing is I still feel like a failure most days, but I try and get through it by just talking to people about my work. The isolation is quite hard, especially during the pandemic, because I don't go into the office all day, but I try and balance it out. But you have to find what's good for you. And sometimes it is just going out and talking to people, having the technical chats, having the non-technical chats, a few drinks here and there that can help reset you and just help you get out of the hole.
Well,
Okay.
thank you for being open and being vulnerable. These are it is very hard to be vulnerable. Like we feel that we can be attacked, right? Like that we're showing our weaknesses, but I believe that there is a lot of strength in vulnerability for the exact same reason,
Yeah.
right? It's how we are able to connect with each other at the same time.
Yeah, and I think one of the nice sayings I think gets banded around in Scotland is, "What's for you won't pass you by." And so the key message from that is, if you cannot get an academic job, that's not the be all and end all. You haven't necessarily failed. And it's a bit contentious, but there's other routes to doing interesting research. And I don't think we are open enough. Well, we might be actually, and I've just not encountered it of that. Industrial research is quite interesting, right? And there's lots of cool things you can do. And I know you've had Dan Geeka on the show. He's the head of PL at Huawei in Edinburgh and professor at Birmingham. And there's other people who've left academia years ago. So from Glasgow, there's a Satnam Singh, right? He left a lectureship to go into industry, and as far as I can tell, he's not really looked back. And we need to normalize that it's okay not to be a professor. Well, he wants to be an ass professor. Right?
And there are many companies that are doing this sort of work. There's Galois, there is Jane Street, there are more.
Yeah.
I know there are, and there are many, like at Galois that I've been there, they have many researchers, there are professors that have gave up their professorship because it is a very tough environment, and maybe we realize that we don't want to be here as well, and that's totally okay. But as you mentioned, you have to find, in the end of the day, you have to find your own answers, although it's very important to seek for help. And the way that I personally look at it, I've also been through some process of burnout, and the way I look at it is that mental health is health, and just like health, once you realize that there is something wrong, then it's already very wrong. So the best way to protect yourself against these things is to work on them before they happen, right? So the same way as health, you go to the gym, you keep yourself safe, you don't get too much cold, you can do similar things to your mental health too. You can go to work on your physical health. You should. I definitely recommend this to anyone who is in academia, anyone who is a PhD student. I think it's a must to be seeing a psychologist, because you will be into a tremendous amount of pressure that you have never seen in your life. And it's important for you to be having professional health early on, because it will teach you how to properly think about these problems, right?
No, absolutely. I agree there. And I think one of the things we're seeing now, so I come from a generation where you don't talk to therapists because that's only for crazy people, right?
Yeah.
But what we're seeing now is being more normalized. And I think one of the things to put into context is the actor, oh God, I should know her name. She's from Inverness, right? Not Gillian. Gillian? She was on Doctor Who, and she was in the Avengers playing Nebula. I can't remember her name. Anyway, it's going to haunt me now for the rest of the day.
I'll put in the show notes at the end of the episode. I'll come back and be like, hey, this is
this one. Yeah, no, well, the whole point is like she opened up on social media that her and her partner were having couples counseling. And when you think about, oh shit, they must be having trouble, I went, no, it's a health check.
Yeah.
right? It's a check to
Yeah.
say, like, it's a check in to say, like, anything we talk about, you hear other people in famous people saying, yeah, we have regular therapy because it's what we do to help our relationships. It's to help check in and to keep you grounded. And
Hmm.
it should be, and I think one of the nice things about the younger generations is that having therapy is more normalized. It's more, it's normalized. There's no stigma attached to it,
Yep.
and that's that's very important to
Usually
note.
the stigmas are kind of personal. For me, I was like, I had to reach some kind of bottom to be like, shit, I need help, right?
Yeah.
But the moment you realize is already a big step too. So I don't know. I shouldn't say that in a way. I'm glad for this because you shouldn't. I don't think you should be glad for any kind of suffering. You can do better without. You can always do better without suffering. But in a way, it was good for me to learn and to be where I'm at, right?
No,
So
that's you're spot on there. It's and the first cut is the deepest. The hardest thing is to acknowledge and then find help.
yeah, acknowledge and
I
find
still
help.
have I still have trouble doing that. I'm not perfect, and mental health for me is a constant battle. And there's days where I won't talk to people, weeks I won't talk to people because it's too hard.
It is, and
Yeah.
it's in a way, it's also how in my point of view how men are raised too, like
Hmm.
we're supposed to go through our feelings and bottle things up and man up and do our stuff, and we
So
don't like
w-
to deal with feelings so much.
one tidbit as being a parent as well in academia, and so things like postnatal depression, uh, issues being a new mother are well studied and communicated in most antenatal programs, right? And this is it's a wonderful thing, they're addressing, postpartum depression. But
Hmm.
what they're not doing is looking at it a lot for men. And you're right, there's a stigma for men that, you're not supposed to go to therapy because that's not what you do. And there's a trickle. And I say a trickle, but there's a trickle of change coming that is letting people of, males to access the mental health services they need. And it's changing slowly, but you're right. Men sometimes do have the brunt of it because there's a lot of social stigma attached to it, machismo. Yeah. So,
Yeah,
right.
these are difficult things to
Heavy
come
topics.
up, and it's heavy topics.
It's very heavy.
Well,
Right.
I'm glad that we had this conversation. I hope that whoever is listening in the future keep these things in mind in their hearts, that don't be where we got, right? Don't let your problems to spiral down to the point where you will burn out, where you get panic attacks, where places that I've been, and they're very dark places, and I really don't want to see this to anyone, especially to my
No.
beloved listeners.
Yeah, and I think just I'll say one last thing is also that don't feel that you have to search out for the help because that's the really hard thing. And I don't think the onus should be on the individual to find the help. And good PhD programs will, and even good working environments will, someday should be looking out for you, your line manager, your supervisor. There should be a pastoral element in their job there, whether or not that person likes it. That needs to happen because the people you are working closely with sh- should have an innate feeling on your good and bad days. I'm not saying that that's perfect or it's always going to happen, but I think we need to look at ourselves and say, look, when you are supervising someone, try and be mindful of how that person is. You're not there, you're supervising them. You don't need to be their buddy. You don't need to be friendly. You need to be working with them.
Hmm.
But you can also be friendly and buddy. I'm not saying you can be, but I'm saying in the bare minimum, you should be spot
Respectful.
respectful, and if they look like they're struggling, is to have the difficult conversations to sort of say, look,
Mm-hmm.
is this working? But do it in a respectful way that doesn't indicate to them that they should fuck off out of
Yeah.
academia, that they get the
Yeah.
help. And
Yeah.
that's something that, that I want to try and do when I start supervising people, is just saying, look, let's be mindful of its tough, it can be a tough environment, and you don't need to harden yourself up, but you need to be, ride the wave that you want to go on through academia and going through the research studentship process.
Does academia have to be this hard?
No, I don't think so. No, I don't think it has to be. I think we do make it because it's, it's how it's been done before, and
Yeah.
people think that's how it should be done, and it's
Yep.
a survivor bias.
Mm-hmm. Mm-hmm.
And we need more people. We need to, like, as a classic, you need diversification of how programs are run, who's running them, and I think there are people in positions that would do wonderful, but they're against a brick wall in trying to instigate change. It's hard enough to have a process be changed, and uh, but I think it'll get there, but maybe not as fast as we'd like it to. But I certainly like the way I look at these things is I want to be a better person, and I want to be, it's this altruistic notion of I want to be a good supervisor. I don't want people to have the same experiences I've had.
Exactly. Exactly.
And that's all I can do at the moment. And if I'm in a position of power, I try and use that to affect good change. But yeah, this is quite heavy, and
I think it's important for us to be talking about these things, because sometimes I feel that other people has similar thoughts and feelings, and in a way they also feel kind of powerless. Like there is nothing that they can do about it, so they keep it to themselves. So
mhm,
the moment that we are here bringing this up, talking about this, I hope that other people will notice that this is also, they're not the only ones who are worried about this, and we coming together, we will be more powerful, right? And being more powerful, ha- we are in a better position to make actual change, even if it's slow, even if it's, you know,
mhm.
tiny by tiny pieces at a time. But someday we get there. I honestly believe that academia right now is sick. We are in a sick place, and I have no
Yeah.
idea how we got here. We need more historians. Maybe I need to study more about this
Mhm.
history of academia.
Yeah. But
But
it's not just a computer science thing. I think it's
no,
more,
exactly. It's
yeah.
not.
And a lot of it will be cultural, relating to how things are done in Europe, how things are done in Latin America, North
Hmm.
America,
Yeah.
Oceania, Africa, and that. And
Yeah.
it's cultural. Well, hopefully things can change.
It will. I have hope. I have hope, and I believe in people. I'm optimistic. All the time I'm talking about, like gloom and doom things, but I am a very optimistic person, and I believe in people.
Yeah.
Having
And
said that,
yeah.
okay.
Yeah, all I was going to say is that we do see the change because you have the, like, sick plan cares, right?
Oh yeah.
Yeah,
Yeah.
there's things. Yeah, and so we've got, that's what I mean. Things are coming in place. It's just
Yep.
sometimes, Rome wasn't built in a day, and it just takes time.
Exactly.
But let's do more type theorying stuff.
Yes,
Ju-
exactly. I think
just
I think we got in a point where we can be hopeful again,
yeah,
and we got to a point where let's go back to type systems and type theory, which what we are originally here for. So going
yeah,
all the way back from, like 2 hours and a half ago, I believe, if I
more or
don't
less.
edit too much out, in your introduction, one thing that really stood out to me in, like overall of your research is, like the overall theme of security, of dealing with hardware. And one thing
Hmm.
that really, stands out in your research is using type systems, powerful type systems, to talk about hardware.
Hmm.
So my question is, what are the gains for hardware and dealing with hardware to use powerful type systems?
Cool. That's a really nice question, and I think to sort of if you're going to summarize what my research angle is, it's always been what I've trying to coin are TyDe systems, type-driven system design, because types are really good at helping you reason statically about your programs, and also dynamically if you look at gradual systems and so on. But there are lots of interesting fancy types out there that can help us reason better about our program. But at the moment, a lot of that is geared towards programs that perform computation. And those programs are based on the lambda calculus, more or less, right? And or variance. And but it's all about, you have your reduction rules so that you take your large program and it reduces to a value. And we have lots of these fancy type systems to describe these programs. But there's another class of languages that are really, really important, which are hardware design languages. So sometimes you see them being called hardware specification languages or hardware description languages because they do two different things, or they do two things at the same time. And so with hardware languages, we have to think like hardware is pervasive. Headphones I've got on have some hardware. The keyboard I'm typing on is hardware. My laptop's got hardware. What else is around me at the moment? My monitor's got hardware. My phone's got hardware. My doorbell has hardware, right? It's there. And so how do you design them, right? And so you get these integrated design environments that let you do things. But at the end of the day, you think like, what are the languages we're using, right? And there's lots of research out there, and I'm not the only one doing this. There's a large number of people looking at this from various different angles. I don't know all of them personally, but we can string off the work. But the whole idea with hardware description language is you are describing, at the end of the day, instead of having a value that is the result of computation, your value is the circuitry that is then going to be placed, either fabricated, so turned into a physical thing, or it's going to be fabless or synthetic and run on, say, something like a GPU or simulated in some system, right? And that's different. So you're not reasoning down to like, folding a list and getting a single value back out. But what you're saying is like you're taking your design, and it's going to be quite an expressive one, and it's quite, my hands are up above my head saying, you got this large thing, and you're going to sort of like take it and take it and take it and reduce it, and that process is called synthesis, to what is called a netlist, which is the circuit level description of what is then going to be placed onto hardware. But there's more stages after that, right? So not only once you've done something, you got the values, right? And the point is why I'm talking about this is to give people the idea that hardware design languages are different to programming languages, right? But they're similar, but they have different means. And so in the hardware is you're designing or you're specifying the physical structure of your design and the behavior associated with that structure. And we love abstractions. And so the lowest layer of abstraction is a netlist, which is basically your circuits that you do in engineering or very basic course, like foundational courses in your degrees.
What do you do in VHDL and Verilog or
Yeah,
netlists?
I'll get that. Yeah. So and so with languages like Verilog and VHDL, and definitely in Verilog, the netlist is a subset of the language that is purely synthesizable and will also need to have primitives that are specific for the GPU or the hardware you're targeting,
Mm-hmm.
right? And so the base language that gets shipped will be different depending on what you're targeting. Like it's architecture specific. But these are low-level languages. It's like nobody wants to write in assembly. Nobody wants to write in Verilog netlists or
Mm-hmm.
VHDL netlists or whatever the result is like. And so the soup du jour of how things go is they are having this thing called high-level synthesis, or some sort of synthesis thing. You go from a higher level language, which is more expressive, and then you're synthesizing everything down to your netlist. And the study of that is quite interesting. So there's some nice work by and it's quite old, not old work, but in the last 5 years by Andreas Lowe, who was at Chalmers and is now at Imperial College doing a research associate position on formalizing like the synthesis from Verilog to netlist in Isabelle, right?
Wow. Mm-hmm.
Right, so that's, but we still haven't got to the types thing, right? But the whole point is that with the types, we can look at providing stronger guarantees about this, about the structure of your hardware, regardless of the level it's at, but also the high level synthesis and the behavior, and translating it down so that what you spit out at the end is correct. And I think one of the most promising people in this field is a PhD student called Rashid Nigam, or Nigam. I can't. Surname is we chatted about a year ago. I still don't know how to pronounce his surname properly. I'm sorry. He's at Cornell, and he's actually got
Mm-hmm.
the Jane Street Fellowship that he's
Oh,
starting.
wow.
Anyway, and he's done lots of cool work with looking at how you can use types to better reason about the hardware synthesis process. One of it could be in terms of memory usage by using affine types. So advanced type systems, so standard type systems that we all love, are structural, and they talk about the structural properties of your program. How all the terms fit together and how it helps you reduce them properly. But the substructural is all about the behavior, and he's been using that to look at memory one. He had a paper many years ago, but he's also got another paper recently, and I forget the conference it was at. I think it was either PLDI. Yeah, it was PLDI this year, PLDI 23. So to talk about hardware is you'll have a clock and things talk. So basically, to think about hardware, think about a graph or a network of signals and wires put together, and you have a clock that ticks, and then signals and voltages are going through your hardware, or you have a clock tick that helps synchronize things. And
Mm-hmm.
one of the cool things he's done with types, because I don't want to talk just about myself, is studying the clock ticks so that you can reason better about, and I think it was the performance of your hardware design at a high level, so that you can create better guarantees about it. And I forget the details of this paper, but that's like a cool way of using types to sort of like, you'd have this high level language that you synthesize down into your netlist to deploy whatever, but the types help with that. Now, there's other formalizations. So Adam Tripala and Clement Claudel were doing things with BlueSpec Verilog and having that full stack design of going from your programming language all the way down to your netlist. Principally, I think they looked at BlueSpec Verilog, which is a more modern take on Verilog, taking what we've learned from functional programming languages. And they take like a rule base. So they're not looking at the individual wires themselves. They're saying like it's all about rules and registers and their interaction, and it's just a different approach. But also, I want to make sure that Clement is also one of the caretakers of the biblio.el Emacs package. So if you're writing your paper, you can look up the DBLP straight away and download the bibtex citation directly into your bib file. It's one of the greatest productivity tools I have for writing papers these days.
What's the name
Anyway,
again?
biblio.el.
Oh, okay. I didn't know
Yeah.
that one. He's always like, I feel that Clement is always doing some amazing tooling for
Yeah.
us. I love that guy.
Yeah. Yeah. So when you're writing a paper, you call the Emacs command dlbp lookup, and you can search from within Emacs to say, look, what's my latest paper I wrote? I write in my name, and it gives me a list of things, and I can just
Yeah.
highlight and then click insert, and
then we'll put it in the bib tags and we'll
yep.
give you the reference over. Wow.
Yeah. I know.
Thanks,
No.
Clement. That's amazing.
Yeah, I know. You learn something new every day. So anyway, so the stuff that I do, right, is the original Border Patrol project, and I've talked about this earlier, was to look at how we can use fancy types to better reason about the structure of our hardware systems, right? And I've mentioned that in the hardware world, you have to think about, instead of just circuits, when you go higher up, you have modules, and modules have interfaces. Now, these interfaces are sets of wires that have predefined behaviors. But at the end of the day, you can't tell the behaviors from the types. And so there's people at Imperial and now Oxford who are looking at using session types to reason about it. But the thing about session types is it's all dependent on the roles, the participants in the protocol. And to help with that in the hardware, well, let's try and encode these interfaces more formally as a type system. Which means is, can you take, and the whole idea that I took it was, can we take the XML standard that describes the interface for, say, a single interface in a module, and a module can have multiple interfaces, up to, depending on the compiler in Verilog, it can be, I think, 2 to the, quite a large number. Right, and it's quite common for, say, one of the standard protocols, AXI. The full version is to have, minimum of, say, 40 wires. But then you might have 2 or 3 AXI interfaces on a module. You have multiple, and so you're talking about 80 wires or 80. So you think about it in terms of imperative programmer or your function you write. That's like 80 parameters to a module that you have to reason about, and you have to reason about the structure. And at the end of the day, Verilog has a very basic view of what a module is, and it views a module, like the interface, as a port that has a direction, that has a type, and that's it. And the behavior is described in these XML files that can get translated, and they can be used for code generation to generate your modules. But that's done by hand. How can we verify? How can we not necessarily verify? How can we reason about it so that it's a correct translation? And we can use types for that. We can use dependent types, types that contain values, to better reason or to better describe what these interfaces are looking at it, regardless of which endpoint. You have to remember, a wire is a cord that has 2 endpoints, but it could have many endpoints. Like, it could be like fan in and fans out. And these interfaces, the direction that they might have, or what they might be specified, the size might be indeterminate, like depending on how it's been instantiated, or it could be polymorphic, or it could be saying the protocol designer saying, well, doesn't really matter, it just is whatever you want it to be because you have user extensions. And we can use types to describe these interfaces agnostic to the endpoint on which they're doing. And then this is the idea we got from session types, which is we can then project it. So you can say, look, I have a wire that is going from the initiator to the target, right? But in the design, it's just saying, well, it goes left to right. But then if you're the interface, so if you're the initiator, then you have to have an output port. But if you're the target, then you have to have an input port. But the standard will say, well, it goes left to right. And so, but we can do these mechanical transformations, but also things, making sure, like the parameterization. So some of these protocols, so the AXI one, they are parameterizing. Like, you can initialize them with different widths. So your bus width, so basically the width of your array. And so the whole point there is that we can use types to have this more accurate description of the specification as a type that we can then transform into another type that is more specific for the module. And the cool thing is, you can already do this in Verilog, but we've now sort of modeled it as a type system. And so in Verilog, you have these interface constructs that you can say, look, here's an interface, but the relationship between that interface and the views on it is ad hoc, right? There's no formal description. I've read the standard, and there's just basically saying it's freeform. You can do whatever you want. And so what we've done with the type system, we can say, look, actually, here's a formal description of, if you want to change the compiler, introduce type checking for this to get this relationship, here's what you would need to do, right? And so that's providing a bit more confidence in that when you have a module, you can say, look, here are these interfaces, what are their standards? And we can say, look, do they adhere to those standards or not at type checking? during type checking, right? Statically before. And why is this important? Because everyone's thinking, well, it's just a type checker, it just takes seconds. Well, great. But a lot of the testing in the hardware world, and I should have led off with this because I always forget about it, is right. You write simulations. As you simulate things, there'll be clock timings that you need to be aware of. There's synchronizations you have to be aware of. And so not everything, like the behavior, cannot be tested statically. You have to simulate it. Some errors might come up during synthesis. And in some hardware designs, and I've not done this personally, but you always hear the stories, it can take hours, it could take days to run. And so by moving things to be a static design time check, then you say, great, I've detected errors earlier. I've got more confidence. I don't need to test it because, to remember, like system Verilog or Verilog designs are basically saying, right, you have a port. It's got a name that matches the name in the standard, but it doesn't matter. You're assuming that you could easily make mistakes in these translations, and you might only detect them during simulation. You might detect them later on. And there's great tools like Verilator and other formal methods that can help with this, but they're external tools. Types can help us bring those external checks within the compiler. And it's not really a compiler, it's a synthesis engine, but in terms of PL terminology, the thing that then generates, that does the synthesis, you can say check it before you have to do these extended tests, these extended simulations. And the thing we have to remember with dependent types, and fancy types really, is they help address the balance of external testing to intrinsic checks. So you can reduce the amount of external checks you can have if you have a sufficiently expressive type system. You're increasing confidence in your design as a static check, and then saying, well, you actually don't need to do these external checks, so we've already done them, right? But there's more to it, right? And so, Rashid's work is really nice. Adam's work. There's also languages like Chisel, and Satnam Singh was doing a lot of nice work at Google. He's now somewhere else. And always interesting, how can we do formal, using functional programming formal methods to better do the design? And the thing, as I said, I'm interested in types, and I've looked at interfaces. Friends are looking at, or colleagues are looking at using session types to help capture that, and we've talked about this before earlier in the last episode. But the other thing I'm interested in is wiring, okay, and orchestration. Now, orchestration is really the name of the game when it comes to designing your circuitry. And I talked a little bit about this at the beginning, and I'll just go back into it and saying, look, you're dealing with circuits. You're dealing with physical resources. At the end of the day, they could be physical resources. Like, you have a port, you have some gate that you want to wire up, literally. And in higher level languages, you don't have this paradigm. It's all synthesized down. But you do have this notion of usage, of connection, right? If you're connecting modules together, right? It's wiring. It's not passing a parameter. You're basically saying, I'm creating a route that values will travel across their nets. And so you want to reason about how you construct these nets, and they're basically graphs, directed graphs. And you want to reason about that. And so Verilator has some tools that saying, look, we can reason about the connectivity of your hardware design. But that's an external tool. And quantitative typing reasons about how often you can use something. Linear types do that as well. Graded types do that as well. And the whole thing that I'm really interested in is like, can we use quantitative typing to reason how well we've connected our circuits together to mimic what you do in real life, but not design a new language, but to take an existing language and retrofit its type system with a quantitative type system so that the designer doesn't need to do anything.
So the quantitative typing is like linear typing, but you can be a little more precise on the number of times your resource is used?
No, yes and no. So quantitative type theory by Bob Achtke is a more general framework that essentially you adorn bound terms with a usage annotation. And that usage annotation essentially has to be what is called a posit, or essentially a semi-ring. We're getting into a bit more maths here. And the semi-ring that is used often, which is one used in Idris 2, because Idris 2 has quantitative type theory, but is with the none one ton semi-ring, which essentially you adorn, you annotate your binders with their usage, with their how many times they can be used. And that in the none one ton semi-ring is it's 0. But that doesn't mean it's being erased, but it's saying it's available at independent type theory. It's available at compile time, but not at runtime. So it's erased at runtime, but available at compile time. 1 means you can only use it once, and omega, the ton, is got unrestricted usage. And that is the basic idea of quantitative type theory. In linear types, it is things that can only be used once, and you do have an unrestricted portion to it, but the quantitative type system does it much more nicely, I think. But the whole idea,
since we're already defining terms, let's also try to define graded typing and session types as well.
So it's graded modal type. So there's some lovely work coming out of the University of Kent, led by Dominic Orchard, but especially his student, oh god, Dan, I think it is, sorry, who's wonderful, who's done some wonderful work on the grade. So in the graded modalities world, is they try and blend the notion of linear and quantity, so that instead of saying something's either got 0 usage, 1 usage, or arbitrary usage, it's got fixed or up to n usages. So it's graded, so you can have more than 1, but you can say you have a restriction. And they've got this language called granule, which sort of looks at what a language with graded modal types would look like. And that's interesting.
So if you say your type, your value is going to be used n times, is it at most n times or exactly n times?
In the graded setting, I think it is at most, but I could be completely wrong here. I'm not an expert in the graded types, but it is something obviously to clarify. But that is a profound difference, because if you have, it's the difference between at most once or exactly once. They look at the Granule project, people. There's a lot of interesting work there, and Daniel has some really nice talks he's given over the years on what their work does and does not do. So with the session types, session types are a really cute typing discipline to reason about your program's communication behavior. So if you program in a language like Haskell or Java or anyone, you get basically a file handle, and you can send and receive to that file handle or to a process, or if it's a network, you can send and receive in whatever order you want. You're not restricted. And so if you want to implement protocols such as Echo or TCP or Kerberos or anything, you then have to analyze your code using a static analysis tool and testing to work out, are you doing the required ordering correctly? Right? And that is the ordering and sequencing of communications and to the correct parties. Now, session types is a typing discipline that helps you reason about your program's behavior by describing. So there's multiple formalisms here and how you encode it, but the easiest one to understand at the moment would be the classic projection-based, which is you describe a global type which captures the behavior of all the participants in the protocol, right? And that is who sends to who sends what choices of messages can you send, and you label them. And you can think of it as, if you're doing ping pong, it's basically saying having two participants, A and B. A sends to B a string labeled ping, and B sends back to A string labeled pong. And essentially that's your echo protocol. And you can say that behavior is recursive. And we call those and that's actually an example, of a binary session types when there's only two participants, but you have more than two, then it's multi-party. And then you can describe various protocols, and there's a limit on the expressiveness of what you can describe in global protocols, and there's a lot there telling you what it is. So the easiest property is that the protocol should be projected by all rows, and what that means is, well, what use is a global type? Because if you're just viewing things from above, high in the clouds, that's great, but at the end of the point, you're going to implement a role. And so you have not the dual, because that's a technical term, but you have local types, which are the result of taking your global type, projecting it, and it's a decidable transformation to go from your global type to the set of actions you, as a participant, need to do to satisfy that protocol. Right? And if you can take a global protocol and project it to all the participants, then you can say, well, it's well formed for everyone who takes part. But there's also other guarantees. So we also, when we talk about session types, we think, well, its protocol is quite simple: send, receive, choicing, all that crap. But there's also things like, will your behavior eventually terminate? Will there be deadlocks? Will there be other issues with the behavior? And so the theory of session types can help you reason about it so that you can write protocols that are known to be deadlock free. And that if you have a synchronous one and an asynchronous protocol, and by asynchronous I mean regardless of the ordering in which messages arrive, that you know that your program will eventually terminate. Not your program, but your communication will eventually finish. And it's a really powerful tool of saying, look, bringing what would be an external check that you would do, say, with a test suite to something that's intrinsic, of saying, I'll just type it, right? And I know that my program's communication behavior is correct with respect to this global protocol. And how you would source that global protocol is a different kettle of fish. It could be, right, let's take your RFC, request for comments, that has, the echo protocol described as an informal protocol narration, and let's transform that into a session type, and then, your RFCs become a bit more meaningful mechanically. And there's lots to do with session types. There's some really interesting work coming out there, being able to model crash, because we all know that communication can fail. And so some of the latest stuff from session types are modeling crashing within the types themselves. So that you can say, design how in the protocol, in the global protocol and the local protocol, what to do when you fail. Not at the transport level, but actually, and hiding it away from the types, so actually incorporating directly within the types. And that's what I think. Was there one other term you wanted me to clarify?
No, that was it.
Yeah. And so these fancy types are really helpful, and by bringing them to the hardware world, we can sort of bring these ideas of, right, let's have your IP cores, which, remember at the very beginning, if people remember well, is you have these third-party IP modules, intellectual property cores, that are being bought in the binary blobs. You connect them up to their modules, and you say, here's the known interface that they have, and you plug them in. But there might be hidden interfaces that are connecting elsewhere, that are, say, binding to something else, that are just exposing something else. There might be a little phone home aspect to it. You just don't know. And so with the session types in the hardware, you can sort of say, look, let's now generate monitors, things that will then, so remember, types are good at doing static checks. There's also the dynamic checks. That's another thing the session types are good at, is allowing you to develop runtime monitoring for your code's communication behavior. So if you see some behavior that is not quite right, and that means goes against the specification, you can then do something about it. You could flag it up saying, this chip's trying to phone home. It shouldn't be doing that. And there's lots of challenges there in not just being able to do the monitoring, but being space and time efficient in when you generate the hardware. Because hardware is a physical resource, and you have a physical finite amount of space, and there's a thing called placement and routing, which is about making sure the length of the wires aren't too long, that things are in the right position to help speed up the signals. And if you're going to add in on these monitors, you can say, well, what's the real estate of your chip? How much is going to be taken up from that? And so partly that is, now I remember it, is what Harriet Watt was partly looking at is that how we can say, if we have a session type description of what your hardware should be doing, how do we efficiently generate the monitors that we can like literally add to the physical chip design and not take up too much space? But there's more to it than that, right? So we talked about wiring and the quantitative typing. So what's quantitative typing for? Well, the thing about that is now if we can reason about usage, and we talked about this in the last episode, which is, well, in the real world, when I connected my headphones to the USB port, it was the final USB port on my laptop. And once I've used it, I can't use it again unless I put in a splitter or a adapter. The same with plugging into the wall, right? Once I've plugged plug into the socket, I can't use that socket again unless I explicitly introduce an adapter, right? Now, in programming languages, everything's by design, unless it's a quantitative type system, is unrestricted usage. So if you want to reuse a variable, you can do it. The type system says no. It says, well, yeah, go on, do it, have at it, right? But in the quantitative world, you're now saying, right, if it's linear, you've used it once, you can't use it again. If you use it again, I'll fucking cause an error, right? And so in the hardware world, that's actually quite useful because now we can start to say, look, if you have your wire is denoted by a variable, and that's got unrestricted usage. So you can sort of do whatever place it wherever you would like it to go with the minimal type system that it has. And the example I gave last episode was if you have a NAND gate and you've wrapped it up in a module, right? And you have two inputs and one output, and you wire one input from your module to both inputs of your NAND gate, and you wire the output correctly up, you've created a NAND gate. Sorry, a NOT gate, because that's how they work. But then you have this dangling wire, the B wire. And we have Verilator, which is a really wonderful tool to do these external checks, say, oh, by the way, you've done this is wrong. But sometimes it's okay to have dangling wires because you just lose information, right? But the point is, what you want to say, and this is what tools like Verilator can do, is saying, look, what was the error? Is the error that you've repeated the use of an input, or you've left something dangling, right? And that's a question I don't think the types can answer, but what they can say is, by the way, you've got a usage violation that you've used this input wire twice and you've got this thing unused, and we are, say, in a linear setting, so it all has to be used once. And that's what quantitative typing, we can sort of say, look, we can do these checks, say, is it well wired? And the cool mathematical property here is that that comes up to be a directed graph, and you can reason about graphs, you can reason about each node in a graph's expected number of inputs and outputs, their degrees. And you can build this nice notion of denotational semantics of saying, look, your hardware design, if you run it, quote unquote, you will generate a graph. And if it's a correct graph, then you can sort of do a correlation between the expected degrees of each node and the found degrees of each node. And you can sort of build up your type system, your quantitative type system, for doing these well-wired checks based on those notion of denotational semantics. But it goes further in that we think about a single wire, but you have bit vectors which are multiple wires. They're arrays, they're actually matrices. They can have wires with wires with wires with wires. And one of the cool things you can do in the quantitative world now, or what I've done, is by saying, right, instead of associating a binder with a single quantity, you map the resource, you create a resource of quantities dependent on the type of the thing being bound. So for a single wire, you've got one resource. For a bit vector of wires, you've got a resource per element in the array. But for these matrices, these vectors, then it's a sort of a cascade. It's an n-dimensional set of resources, each doing these fine-grained tracking. And so if you say split wire or you index an array to say, look, I want to use one element but not the rest, you can do this fine-grained tracking and use the quantity to say, look, has that been used? And if it's been used, you can't use it. But if it's been not used, right, have it, use it, but then make sure you keep track of the resources that you're using. And that's what the quantitative type theory designs help you with, is that type level tracking of how things have been used. And what's cool is, right, we know we can do this for netlist, but if you want to go higher, and that by higher, I mean if you want to go increase your level of abstraction by doing modules or different data types, is we know we can do this similar resource tracking. Well, by we know, I mean I've got unpublished work that can't get published because of reviewers. That sort of tells you the story of saying, look, let's go a bit further. Let's introduce modules. Let's keep these. What does that mean if you have modules and that you have abstractions, like as you would do in, say, the lambda calculus, and do these resource mappings, right? But what you also get to the point is that if you go very high up to these orchestration languages, you see the same problems of you want to wire things together, but this time you have data types. You might have enumerations, you might have structs and unions, and you still want to do that same sort of resource tracking in those settings. And you can either take a whole view of saying, well, look, let's treat it as these data structures as a single wire, which you can do, and do something, the same special thing you can do for vectors. But in the hardware world, some types can be synthesized down to the level structures. And what you may want to do is to say have some more advanced mapping of that your record actually is not, and if it's a packed structure, then you know it takes up a contiguous section of memory during the synthesis. And then you can sort of look at saying, well, look, we've actually can treat it instead of just a blob, a singular blob, we can actually decompose it into a set of vectors. We can index it. And there are certain conditions in which you can treat data structures in Verilog, system Verilog, as an array of bits. And the cool thing about type theory is we lean heavily on mathematical structured programming and mathematics, and you can sort of describe all of the properties that allow you to say when can you treat your data structure as something else mathematically using lattices. That's something I haven't published yet because there's not enough work to make it into a full-blown paper if you're just talking about data structures. But there's lots of. But the whole point is what we're doing with the types is we're finding interesting parts of how you design hardware and using types to shore up, to make it a bit more verified, to reason about it a bit more so that we no longer have to do external checks. Or we are explaining a bit more formally how the language actually operates. And that's, I think, quite cool.
It's very interesting. Do you guys do some proofs over those types? Because since now you're working with Idris, you can have even more guarantees by proving those
Yes.
properties that
Well,
you could have even do that, like as you mentioned, Verilator. I believe that Verilator is able to verify some properties, right? Like it has some very
yeah.
powerful
So
SMT solvers.
so I've not looked into that in depth because what I've been concentrating on is what I call a resource-dependent type system, and modeling those within Idris as well, or intrinsically typed data structures. And by doing and this is what I've mentioned again last episode, was just, if you can have a well intrinsically typed data structure that captures your language and the typing rules, doesn't make it correct, right?
Mm-hmm.
You have to prove soundness and completeness for your type safety property. And what we've done is a denotational semantics. We've taken a definitional interpreter approach, and which is essentially denotational semantics, by using the language and translating it into a graph and reasoning about the graph, which you can get the soundness result there. But still, you want to be able to say, look, can you actually type check it? Because just because you can build up a model doesn't mean it's correct, And this is where the elaboration comes in, of taking your raw untyped terms and using the power of dependent types to build the evidence, the witnesses, that you can build an instance of your intrinsically typed term. Because if you can do that, you've type checked it. And if you've type checked it, well, you can ship it. You can do things with it. In this case, you can do the not external check. You can do the check that is it a well-typed graph in the graph instance. But if it's a language, like a regular programming language, you can sort of go down into the proofs of progress and using the proofs of progress and preservation to generate the evaluator. Right? And that's one way of using proof of computation. But for the hardware one, it is more of a, we can build a certificate that shows you that your design is well typed. And by well typed, it means everything's been used once. And that certificate at the moment is graphviz.file. But you can sort of think about it as it's producing evidence that can be checked externally. It could be something that we've chosen to generate a dot file, but it could be something that SMT solver could be given, or something else, for the external checks, and that's you going back to proof carrying code, right?
Right.
Yeah.
Another thing that I had in my mind is that in hardware, you guys say that you are synthesizing your chips, right? You are writing down the specification and then you synthesize the specification down to your hardware. What are the key differences between the synthesis and compilation?
That's a very nice question. So the difference, if you're looking at compilation in terms of programming languages, is you're going from a language instance, an instance of a language, which is terms, which you can compute with, and you have these small step semantics, or maybe big step semantics, depending on what you want to work with. But operational semantics that tell you, look, here are these terms that will introduce values, and here are these terms which are called eliminators, which will reduce values down, or reduce terms down, sorry. And the whole idea there is that when you're doing compilation, at the end of the day, you're taking a description of what the computation is, and you're running that computation until you get a value, right? And so you're taking something that is large and you're reducing it to a smaller form. Synthesis is similar in that you're taking a large description, or more, not large, that's the wrong term, of you're taking a high-level description of your hardware, and you're not necessarily reducing its size, you're transforming it from a high-level set of descriptions into a more lower-level descriptions that actually might be more verbose, which could be, and you will end up with files that look larger than your original program, because that's the point of high-level synthesis. The high-level synthesis to do things easily. You're abstracting away from the hardware so you can write things more efficiently, and doing the transformations, the synthesis, going from your for loops and your conditionals into something that's much more conducive for generating, or I say generating, but for going onto hardware. And there's more stages after once you've generated the netlist, there's more stages afterwards. But the whole point is synthesis, in the terms for that, is taking your high-level description and transforming it, but you're not necessarily getting smaller. Compilation is all about reducing to a value. Synthesis, as far as I'm concerned, is you're not reducing to a value, you're transforming into a value. But that value just happens to be a netlist. And Andreas Loh's thesis, as I mentioned before, is a good one. Oh, not thesis, sorry, paper, is looking at that synthesis formally in Isabelle, going from a high level, not high level, just going from Verilog and showing you how to generate the netlist and doing that formally. And that's quite nice. And there's other works. John Wilkerson from Imperial, his group has done some nice work on looking at taking cues from the CompuCert project and doing more formal high-level synthesis of going from your code written in C and generating the net lists and the Verilog, incorporating, I think, Andreas Lowe's work. And so that stuff's done in Coq. And so, I think a key takeaway here is, theorem provers are not just for programming languages, they're for other languages as well. But we already knew this, right? If everyone's followed Adam Tripala's work and Clément's work, we all knew this already. And I think my little bump of knowledge here is that, oh yeah, let's use dependent types to help with that in a language that is not necessarily geared towards theorem proving in the first instance. And that's one thing we have to remember with Idris and Agda and Coq is they're different languages for different scenarios. So Coq is a really great theorem prover. That is done in one style. Agda is a really great theorem prover that can do general purpose programming, and it leverages dependent types in a very different way compared to, say, Coq. And Idris is a general purpose language with the dependent types that can be used for theorem proving. I think that's something to point out, that what I'm doing is saying, look, we can build practical systems, we can reason about them, we can do the formal methods that, say, people might do with Isabelle, but we're doing it in a language that is more conducive to programming than it is to, say, theorem proving. But we can still do theorem proving.
And that changes everything, right? Because then once the developers, the people who are building Idris, have this goal in mind to be a programming language, right? Like to really facilitate usage of programming language things. I really appreciate that you did this distinction. I have never thought of this, like the big three. Nowadays there is also lean that I would say is even more for mathematical reasoning nowadays.
Yeah, and lean 4 is written in lean, so it's
right.
They are self-hosted, and Idris 2 is self-hosting. It's been that for a long time, and there's some interesting notions there. I think
Coq is almost self-hosted with the work they're doing with Metacoq.
Yes,
I think they're almost there.
Yes, almost there. But I think the main thing is that all of these projects do different things, and no one project is better than the other. They all have different goals, and we work as a community to advance the state of the art. And and that's it, right? It's basically anything you can do, we can do better, and vice versa. and it's having that development race, contention that's saying that does that, and we can explore different ways of doing things. And the thing I like about the Idris project is not because that was the first one I got introduced to, is that notion of all the work I do, I run it. So I talked about the netlist and orchestration language and that, and I said, look, we targeted. The idea is that you have your subset of Verilog that is understandable by Verilator, so you can just check it. Well, my tool understands the same thing. You can do the same thing in Isabelle, right? But the whole point is that we've got we're not just saying generating EDSLs within the language. We're using them to build verified compilers. And I'm aware you can do the same thing in Coq, you can do the same thing in Agda, and Lean itself. And that's the next step. It's not just using the Coq IDE or VS Code now to do your theorem proving. And also to build the languages, but you're saying, look, you're building programs that are verified, that do the job they're supposed to, and you can reason about that. And that's much nicer than just say, oh, we've just mechanized our proofs of progress and preservation, saying, well, actually, the next step is can you use that to do something practical? And then the interesting question there is, right, so I've got this language I'm working on at the moment called Kipple. It's going to be done by definition interpreters, but if I use reductions like operational semantics and do that, it's not the most efficient implementation. You've got all these compiler optimizations, right? So I build functionally correct compilers. Let's build functionally correct, efficient compilers. And dependent types can help with that. And that's a cool thing to explore is, how can we take our functionally correct programs and make them really, really efficient. And Erasure helps with that because you can get rid of all the cruft that you don't need at runtime because it's only used at compile time. But you can also do tricks there on how to be really efficient and smart about what objects you're reasoning about and what they will look like at runtime. And there's a whole other set of hour or 2 hours worth of material we can talk about there, right? Because this is the cool thing about the dependent types world. It's not just doing things correctly; it's doing it correctly with eyes on efficiency. And that is, it's like, and that's quite cool. We can say we have a PLDI paper that is formally verified and efficient, and not just we have something that works but it's not efficient because it's an implementation detail. Saying like, the thing we formally proved is actually comparable to existing tooling, and that's the thing that I've saw with some of the work that I'm presenting at eCoop in a couple of weeks is that is we are comparable as far as we can tell in the small in the testing we've done. It's indicative, and that it all looks comparable to what you can do in Verilator, right? But we have these much more fine-grained checks, and right, that'll probably blow up in my face, and it's a claim I shouldn't really make. But the whole point is that if you look at Idris's test suite and the stuff it's doing, and some of the checks it's doing, or you look at some of the stuff we can do in Idris and Agda and Coq, it's probably that probably used to be slow, but now we're getting faster. We're working out the techniques we are able to apply to reason about things more efficiently at compile time, so when it gets to runtime, we know we can get rid of it, which means our programs can run faster. Like my dream, and I know I ramble on a little bit, but one of my dreams that I would like to have as a student project is, can we omit Haskell 98 from Idris 2's compilation? Like, can you compile something, erase it, and have it look like a nice clean? You can't do this, right? Or you probably could, but the whole point is to show you like your erased program looks something nice. But then the whole point with the pipeline in Idris and all the compilation steps is there's lots of stuff and it gets erased. But the whole point is when you erase something, the hardest thing to do is to look at what's been erased as the output from the compiler and what you've put in and work out what's left and have a more nicer view of that would be actually quite cool to say, look, your nice high level program with all the dependent types gets erased into this really simple Haskell 98 style program. But we're not going to get there, but as a pipe dream, right? To sort of show you the eraser in action, that you can actually erase something and then what gets popped out is something that's clean, but it's a result of compilation, right? So it's correct.
Coq has a extraction feature, and it's not clean at all.
Yeah.
It's a very messy code, but I think the main goal there is to be able to just run your code.
Yeah, that's
right?
the same in Idris as well, right? I've looked at the generated JavaScript, I've looked at the generated scheme, because it's got the Shea scheme as the workhorse for the runtime, and it's not pretty, but it's not designed to be pretty. It's designed to work, and that's why I said it's a pipe dream. I would love it just to say, like, you take your programs and just you see clean data structures, you see if you're doing your list with length, vectors, right, and the whole library gets generated, but it's just turned all into lists because you just erased all the type level stuff. But we're not going to get there, but it's also a good learning thing to say, look, well, what is and what isn't erased.
That's the hard thing about compilation and translation between languages, is because it's very you need, at the end of the day, you need a recipe, right? You need a program to do things in this particular way, and things can get very complicated because of that, because you're trying to chunk down things in a very specific way so that the final code can get very messy because of that. Maybe here's an idea: use something like ChatGPT to look at that code that is messy and be like, okay, how can we transform this to something that is more intelligible?
Yeah, I disagree on that. I think there is a role of AI here, but not necessarily in terms of large language models, but more, can we analyze our programs and work out what is needed and not needed? So to provide a bit of background, so QTT is really nice in that it's user-defined annotations on your terms. What's used, you decide what's used at runtime. There are
QTT is
defaults.
quantitative type theory.
Yeah, quantitative type
Okay.
theory, right. Right, that is user-guided annotations. So their Idris 1 didn't have that. It had erasure inference or synthesis. So Matush Shekzek, Edwin's PhD student, designed TT star, and that was an ICFP paper a few years ago. And the whole idea there was that his compiler, his type checker, would work out what was used at runtime and work out what wasn't required at runtime. And here we're getting to the notion of, type synthesis, type checking, and that can we use the types to infer more information about what our programs do and don't do, and when they do and when they don't do it. So if you want to do cleanup of your code and work out what's redundant, can we design new type systems or use new modes of your type system to make these decisions for us or help us?
Mm-hmm.
So if you can rewrite something, basically rewriting, well, there's whole rewrite rules for introducing performance, like skeletons, right? And those are essentially rewrite rules on how you do code transformations, program transformation, right? And if they can be type directed, then you joke about it, like you have a program that makes our code better. Well, yeah, but you don't need large language models for that. There's things like constraint checking. There is a whole area of AI that is not this fancy stuff that everyone thinks is sexy, right? There's stuff that it's low, it's practical, of saying can types help with there, so Nadia
Polyparkova.
Polyparkova, thank you.
I might have butchered, but
I was going to say Polyakov, but that's coming from Tinker Tailor Soldier Spy, right? She looks at program synthesis, and can we use types there to help with that? Or can the types with expressive type system, can we use quantitative typing, or those like inference? Can we infer things from our languages, build new types, and do these analyses for us? But not necessarily using external, but doing new types for this. And I think that's an interesting direction because Matish's work was able to infer erasure, and sometimes the inference got it wrong, and sometimes you'd want to do annotations to say, look, this has to be erased. And this is getting into the notion of one of my current things I like thinking about is bidirectional type checking. And that'll probably be a third episode. But the whole notion there is, when it comes to things like type checking, is can we use this notion of synthesis, type synthesis from terms, checking with known information, to learn more about our programs and what we can do with them, especially if you have more advanced type systems like things with quantities. Okay. And that is, that's my retort to you saying, I'll just use ChatGPT to translate your program, saying, well, actually, we've got the tools for it already. It's just we need to do, if you're doing program synthesis, that's generating programs. You can do it from types. Well, what if you have more advanced types? Well, what does that give you? And we forget when we talk about languages like Idris and Agda, it's their program synthesis tools, the interactive development.
Yep.
Right. Last time I used Haskell, I missed case splitting. I missed automatic insertion of case constructs, automatic dependent case insertion, lifting, typed holes.
Yep.
Typed holes are cool, and filling holes is cool, and and the nice thing about Idris 2, right, is you can have your vector append and say generate me the complete definition for it.
Right. Yeah.
Right. Because the quantities help there.
Yep.
So if you want to do program rewriting and make things more efficient, or just do any sort of analysis, this is not stuff that I that's not my bread and butter, but it's something that is like, this is really cool when you think about it. Is can we start writing or having a conversation with a compiler? If I give it sufficiently advanced specification, what can I do to help it generate the results for me?
Mm-hmm. Because that's the thing, the more typing you have, the more information the compiler have to assist you. I think that's the main spiel that Edwin gives about Idris, right? Like because the compiler has a lot of information with dependent types, and he can assist us to do our work. I have a question. This code that you were doing in Haskell, did it compile because it was missing a case? Because I remember that it used to compile back in the day. I'm not sure if it compiles anymore.
I don't know. I can't remember because I got frustrated.
I believe this is called incomplete pattern matching, or
I think that's turned on by default. I gave up and switched to Idris after all. I was playing around with something and I thought this was, quite frankly, just trying to remember Haskell and learning a bit more about Haskell because I haven't done it for a long time, especially if you want to do teaching. And I thought, all right, I just do it in Idris and then just translate back.
So before we finish, I think we have covered a lot, and I'm pretty satisfied. I don't know.
But there's a lot more we could talk about, but let's save that for episodes 4, 5, and 6, right?
Of course, yes. So I think we can stop here, and then we save a little bit of meat and a little bit of content for the future.
Yes, indeed.
Well, so thank you so much for coming, Jan. I think this was an amazing conversation. I am very, very happy with everything that we talked about. We touched some very complicated subjects in the middle, particularly. I'm happy that we did it.
There's lots we haven't talked about as well. And so there's lots of cool things with things like gradual typing that is coming in the mix. And the main, that's the thing, we can talk till the cows come home with this. But I'm actually quite happy to have the opportunity to talk. It was a little bit serendipitous because you had Jesper Cox on a while ago, and I thought, oh, that's cool. I like talking about dependent types. Where can I talk about it? Because I don't think the Haskell podcast would be quite right because they talk about Haskell. I don't do Haskell, and it's been nice coming on here because I feel that, as I said about the mental health thing, it's good for me to chat about something to get things off my chest.
Yep.
And if that can have some impact on the community, like talking about community structures, getting some bigwigs in our community to say, Jan, what's fucking wrong there? Let's tell him why. And I think that's good because it gets the information out.
Yeah.
Because if it can be corrected on record. But no, it's been nice. Obrigado.
Muito obrigado. Well, so with that, we finished this episode. Thank you again.
No, thank you.
Well, that was it for today's episode. I hope you guys enjoyed as much as I did. Jan is a really cool guy. I'm really happy that we have this conversation. So anyways, if you guys have any questions for Jan, leave it in our website, typetheoryforall.com. You can send them in our email as well, typetheoryforall@gmail.com. Don't forget to like and share this episode with your friends. We also have a Twitter. Make sure to follow us at TyDe. Every now and then I'm trying to make some dank memes for you guys. If you have any memes ideas to send me, I will be happy to take them and make something out of it. Or at least try. I don't know. I'm not that creative, honestly. But yeah, don't forget to join our Discord as well. You'll find the link in the website. And did I forget anything? I don't think I did. That's it. Thank you a lot for listening. See you guys next time.